Hello again. In this video, I'm going to go over section 2.7, part 3. And what we're going to do in this video is we're going to use the epsilon delta definition of the limit of a function to prove that the limit of f of x as x approaches a is equal to L. So let me remind you of what the epsilon delta definition of the limit of a function says. So it says the limit of f of x as x approaches a is equal to L if for any number epsilon greater than 0, there is a corresponding number delta that's greater than 0, such that the distance between f of x and L is less than epsilon whenever the distance between x and a is less than delta. Okay, so we're going to use that epsilon delta definition to prove that this limit is equal to 7. Now I know we already know how to find this limit, right? We can find this limit using direct substitution because this is a linear function. Okay, so if you plug 2 in for x using direct substitution, then you can see that the limit of this function as x approaches 2 is certainly 7. But we're going to prove that using the precise definition of the limit of a function, right? The epsilon delta definition of a limit. Okay, so let me run through that proof. Okay, when you prove the limit of a function is equal to L using the epsilon delta definition, the first thing you've got to do is start with epsilon. So we're going to let epsilon be any positive number. And what we have to do is we have to show that there's a corresponding delta that will satisfy this statement, the statement in the epsilon delta definition. Okay, now we have to prove this or show this for any positive number, which we're calling epsilon. Okay, we have to, for any epsilon that's positive, we have to find a corresponding delta that's positive, which will make this statement true. Okay, now the hardest part when you work with these epsilon delta definition proofs, or epsilon delta definition of a limit proofs, the hardest part of this is knowing what to pick for your delta, your corresponding delta. But I'll tell you this up front. For linear functions, delta will always be epsilon divided by the absolute value of m. Okay, and so for us, our linear function has a slope of 3, and so it's going to be epsilon divided by the absolute value of 3. Okay, so we're going to pick our delta, our corresponding delta, to be epsilon over 3. Okay, that's going to work, and I'll show you that this works. Okay, so I will admit, if you've never done this before, you wouldn't really know what to pick for delta, and you may have to play with it to figure it out. But I'm telling you up front, for linear functions, delta will always be epsilon over the absolute value of the slope of the linear function. Okay, now for any positive epsilon greater than 0, I'm claiming that if we pick delta to be epsilon over 3, that will satisfy this statement. Okay, so let's prove that. So let's say the distance between x and a is less than delta. Okay, so if the distance between x and a, now a in this case is 2, right? A is the number that x is approaching, so in this case it will be 2. Okay, so if the distance between x and a is less than delta, and we're picking delta to be epsilon over 3, then what does this tell us? Okay, let's see. Well, if this is true, then if I were to multiply 3 on both sides here of this inequality, then this would be true. Okay, I'm just multiplying both sides of this inequality by 3, right? So if I multiply both sides of this inequality by 3, then this would be true, correct? Now notice I don't have to flip the inequality because 3 is a positive number. Okay, the next thing I'm going to do is say that if this is true, then this is true. And that's simply because the absolute value of 3 is equal to 3. So these are the same thing, essentially. Now, the reason I'm doing that is because we know the absolute value of A times B is the same as the absolute value of A times the absolute value of B. And so now I'm going to say, well, if this is true, then this is true. Okay? By this property of absolute values, right? So the absolute value of 3 times the absolute value of x minus 2 is the same as taking the absolute value of 3 times the quantity x minus 2. So if that's true, then this is true. Okay? All right, well, if this is true, then I can distribute the 3, and I'll get 3x minus 6. And so the absolute value of 3x minus 6 will still be less than epsilon. That should still be true. I just distributed the 3. Okay? And then if this is true, then what I'm going to do now is I'm going to try to write this so that it looks like f of x minus L. Okay? Well, f of x in this case is the 3x plus 1. Okay, so 3x plus 1, that's my f of x. Minus L, L is 7 in this case. Are those the same? Sure, 3x plus 1 minus 7 is the same as 3x minus 6. So if this is true, if the absolute value of 3x minus 6 is less than epsilon, then the absolute value of 3x plus 1 minus 7 is also less than epsilon. Okay? So if that's true, then this is still true. Okay? But the reason I'm writing that is because this is f of x. Okay? And this is L. And now we're done with the proof. I've proven it. Okay? So let's see why I've proven it. I just showed that if we pick delta to be epsilon over 3, then anytime, right, if anytime the distance between x and 2 is less than delta, which is equal to epsilon over 3, right, anytime this is true, then this is true, this is true, this is true, this is true, so this is true. So if this is true, then this is true. Okay? In other words, okay, i.e., another way to write this is to say that 3x plus 1 minus 7, or sorry, the distance between 3x plus 1 and 7 is less than epsilon whenever the distance between x and 2 is less than delta, which is equal to epsilon over 3. Okay? And that's what this epsilon delta statement that we had to prove, right, says. And we just proved it. Okay? So it says the distance between f and L must be less than epsilon whenever the distance between x and a is less than delta. We just proved that. We just showed that the distance between f and L is less than epsilon whenever the distance between x and a is less than delta. Okay? So this is our proof. We just proved it. Okay? So like I said, generally the hardest part of this epsilon delta proof that we did here is to pick the correct epsilon. But again, for linear functions, delta will always be epsilon over the absolute value of m, okay, the slope of the linear function. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.